Friends, welcome to the second lecture on module 2, which is focused on accident modeling, risk assessment and management. In this lecture, we will talk about chemical exposure index under the course of HSC in offshore and petroleum engineering, which is being dealt at NPTEL IIT Madras. Chemical exposure index is a very simple method of rating the relative hazard to people residing in the neighborhood of chemical process industries. CEI, abbreviated for chemical exposure index, gives actually a risk index value which is relative to various safety and environmental characteristics of a given process industry. It can be used for risk ranking of various options of safety aspects in a process plant. Nevertheless, it can be applied to oil and gas industries as well. This index value, which is an outcome of CEI study, is used along with the decision analysis tool. It is very important. The risk ranking, which is derived as an outcome from the chemical exposure index, cannot be applied because it is only applied locally to a given problem. Now, if you want to take any decision based on the risk ranking derived from a chemical exposure index study, then you have to apply a decision analysis tool to check the process options in the terms of safety. Now, the safety in this case is applicable to both personnel and process. Now, the question asked in mind is, to do a chemical risk analysis, what data do we require? We obviously should have the plan of the process plant and details of surrounding area, because as I said, chemical exposure index deals with the personnel safety. It also requires to arrive at the societal risk developed or imparted by the process plant in the neighborhood of the locality where the plant is situated. Therefore, we should have the complete geographical details of the plant, plus we should also have the climate, weather conditions and the population of the surrounding area where the plant is situated. So, you should have the detailed plan of the working process of the plant and also the details of other plants located in the surrounding area. Obviously, one should have the details of flow sheet, which involves major piping in the process plant, containment vessels, chemical inventories which are located in the plant and also in the plant located in the neighborhood of the process industry. We also have to look at the details of physical and chemical properties of the material which is being investigated. So, there is chemical engineering handbook available in the open literature where the physical and chemical properties of various chemical inventories are available in a tabular form. Most importantly, friends, one should also have something called ERPG values. ERPG stands for Emergency Response Planning Guide, which indicates an ERPG value associated with every chemical inventory which is applicable to any process plant. We should also follow the guidelines indicated by the chemical exposure index study, and of course, we have got to fill up what is called as the CEI form, which is a standard format of reporting the chemical risk analysis of any process industry. Before we look into detail of chemical risk analysis, let us look at the overview of risk assessment techniques that are commonly practiced in offshore oil and gas industries. There are broadly two kinds of techniques which are practiced in oil and gas industry. One is called qualitative, other is called quantitative. When you talk about frequency analysis, you can also do the model effects and also estimate the likelihood of these effects. You can also do something called consequence analysis, which also gives the model causes and estimate impacts of these causes on the given body or on the given neighborhood. Both of them are techniques available which are essentially allowed for identifying hazards in a given plant. Friends, we all remember that hazard is a situational scenario. So, to identify an hazard in a process industry is the most difficult task. The fundamental reason being this is process changes or diverts under given operational temperature and pressure which cannot be expected unless otherwise that OTP is reached in a given plant. So, to identify hazard in a given process while the process is in operation is the most difficult task. Therefore, people generally do either a frequency analysis or a consequence analysis to estimate ultimately the risk. So, one can see here hazard is getting materialized into a risk because you have effects and you have likelihoods, which is frequency, you have consequences. So, product of these two joined together will give you what is called risk evaluation. Now, under this whole process there are certain segments which are qualitative, there are certain segments that are quantitative. Now, when we talk only about the model effects and model causes, we address this as qualitative method, that is why we call qualitative ranking of recommendations can be derived only from this. Whereas, when you look at the estimate of likelihoods and estimate of impacts which are reasons or end products of the cause and effects, then one can also do the quantified benefits and cost of risk reduction alternatives, because now you have a number by which you can do a risk ranking, then you can also know the cost justification towards risk reduction effects, which is otherwise an important factor in Allard triangle. So, the one when we talk about conversion of qualitative statements into a number, we quantify them, we call this as quantitative techniques. Therefore, risk is a part of quantification of hazards, whereas qualitatively also you can study hazards, which is for example an hazard report. Now, once you do the risk evaluation, it will ultimately land up in absolute and relative risks of given departments or given process plants. Can also identify, or rather one should be able to identify distinctly the major risk contributors in a given plant. You should also be able to compare the contributors of the present risk of a given plant with that of the other risks which has been found in other plants or other segment of the plants. So, risk evaluation gives an overall picture of the entire plant, either in the segment wise of the plant or for the complete plant. So, this will help people to really know where is or what are the factors or what are the common segments in the given process industry that contribute to the risk to the maximum. So, if you really wanted to invest on risk reduction, risk mitigation or risk control, etc., then one should quantify them in terms of numbers. So, one has interested in doing the risk analysis in detail. Hazard analysis will not help you to quantify or at least to find out the cost benefit of risk reduction methods if you do not quantify hazards into a risk format. Therefore, both qualitative and quantitative are vital in an offshore industry. Unfortunately, both of them are adjectives as QRA. QRA can be addressed as qualitative risk analysis or quantitative. The moment I say risk analysis, please understand it is always quantified. Therefore, if you see a literature talks about QRA, it is very clear, since RA refers to risk analysis, the term Q refers and have to obviously refer to quantitative methods only, because risk is quantification of hazard. Please understand, risk will try to give you a number which is always called risk ranking, which is very beneficial to identify the risk characterization locally and globally for the entire plant. Once we understand risk methods or quantification of hazards, then let us see what are the common methods of risk assessments and where chemical exposure index method do lie in these differences. If we talk about hazard identification methods, one can do literature survey, one can do what if analysis, one can also perform safety audits, you can also conduct what is called walkthrough survey and prepare a checklist, or you can conduct a brainstorming workshop to identify the hazards present in the given plant. Of course, more advantageously one can do a HAZOP study and FMEA studies, which we have seen in the previous module with examples in detail. All of them are called hazard identification methods. However, all of them mostly are qualitative, but FMEA is converting a qualitative statement into a quantification by what is called risk priority number. The moment the risk is associated in any study, please understand it is getting quantified. Followed by which the other method of risk assessment is consequent assessment methods. We can also do source term modeling, atmospheric dispersion modeling, blast and thermal radiation modeling, aquatic transport modeling, effect models and mitigation methods available for modeling. All these only talk about the consequence of a given source of an hazard. Consequence alone will not help us. We should also know what is the frequency of assessment. One can do historical records, one can do fault tree and event tree analysis, one can also do an FMEA. Please understand, in frequency assessment methods which is getting quantified slowly, FMEA, which was an hazard method, is also available in FAM, that is frequency assessment methods, which is quantified. External event analysis can also be performed to do frequency assessment methods. Ultimately, when you have the consequences, when you have the frequency, one can result in what is called risk evaluation, which is an FN curve, development of risk matrix, which we already saw, risk profile, risk isoplets, development of risk density curve, and ultimately calculating risk index. So, if you look at different methods of evaluation of risk assessment in terms of hazard identification, consequence assessment, frequency assessment and risk evaluation, the one which is red bordered here are all part of chemical exposure index. So, chemical exposure index do detailed hazard identification of a given process, pick up the source term modeling for consequence, identify the common causes for the failure in a given system, then ultimately land up in deriving what is called risk index or ERPG. Therefore, chemical exposure index is a quantified method of risk assessment which gives me ultimately a number based on which the risk ranking of the given process segments or the whole plant can be done. As I said, chemical exposure index, which is one of the quantified risk assessment methods which deals with chemical risk analysis. The vital part of chemical risk analysis is ERPG, Emergency Response Planning Guide. It talks about different levels of emergency response planning. Let us see what are these levels. ERPG values are estimates of concentration ranges where one might observe adverse effects of chemical on biological organisms. ERPG level 1 is the maximum airborne concentration below which all individuals could be exposed to that concentration for a period of 1 hour. They shall experience only mild health effects, they will not experience even objectionable odor. On the other hand, friends, please understand, ERPG level is trying to quantify the concentration of the chemical for a specific duration of exposure for a period of, let us say, maximum 1 hour, and the consequence of this exposure on the biological organism should not deal to mild or serious health effects, should not even cause objectionable odor. So, one can easily realize that a chemical dispersed in environment with a very moderate or very mild concentration which will not cause serious health effects, which will not even result in objectionable odor, is what is called as ERPG level 1, provided the human being or biological organisms are exposed to that mild concentration which is airborne only for a maximum period of 1 hour. So, please understand, friends, when you declare ERPG concentration levels, there are two important things here. One is the concentration itself, second is duration of exposure, and third important hidden agenda in declaring ERPG level is what are the consequence effects of this exposure on biological organism. If the exposure does not cause serious health effects, does not even cause objectionable odor, we can call that level of concentration as ERPG level 1. So, for every chemical, ERPG level 1 concentration in parts per million or milligram per cubic meter is available in the standard data book of chemical engineering. Similarly, ERPG level 2 talks about maximum airborne concentration below which all individuals can be exposed to 1 hour, but these individuals will experience health effects but are not irreversible or serious in nature. So, they will undergo or experience certain serious health effects, but they are not very serious in nature. So, ERPG level 1, level 2 as well as level 3, all the 3 ERPG levels only talk about the maximum airborne concentration. Please understand, chemical exposure analysis which deals with ERPG does not talk about concentration in water body, it is only on airborne concentration. It means if the chemical is released in atmosphere, when the chemical release becomes airborne, what is the maximum concentration which will not cause serious health effects, which will not result in irreversible effects, which will not result in life threatening effects, and to the maximum duration of exposure is 1 hour in all the 3 cases. For all ERPG levels of 1, 2 and 3, the maximum permissible exposure to this concentration is only 1 hour. So, this is common in all the 3. Which is not common in all the 3 is the effect of this concentration on the human being. For example, ERPG level 1 does not cause even objectionable odor, ERPG level 2 will not cause irreversible effects, whereas ERPG 3 will result in life threatening health effects. If you do not have ERPG values for the given chemical concentration in the chemical engineering handbook, then there are substitution values available for ERPG also. When established ERPG values do not exist for certain chemicals, following values are recommended in the same order of preference. Instead of ERPG 2, you can use workplace exposure guidelines given by Dow IGH, ACGIHTLV or AHA wheel. Otherwise, alternatively, one can use STEL, which we already seen in the previous lecture, of any ceiling value if it exists for the chemical, or alternatively you can use 3 times of time weighted average of the chemical concentration in place of ERPG2 values. For ERPG3, you can also look for lethal concentration 50 value of the chemical divided by a number simply 30. Alternatively, if you have ERPG2 value for a given chemical concentration, multiply that value by 5 times, you can take that as an ERPG3 value. Remember, ERPG level 1 is the mildest concentration, ERPG3 is the maximum concentration which will cause health effects, which you can see from this slide. ERPG1 is the mildest concentration because it cannot even have an objectionable odor. ERPG3 can result in threatening health effects. So, ERPG3 value is simply 5 times of that of approximately ERPG2 value if ERPG2 and ERPG3 values are not available for a given chemical in the chemical engineering handbook. If you really wanted to find out ERPG1 value equivalency, then you can use odor threshold value or take ERPG2 value from the literature, divide that value by 10. So, mild, medium and severe. So, why I am putting them in this order is, this is how OSHA recommends substitution of values of ERPG for given chemical concentration if it is not available readily in the literature. Now, let us see what are the different scenarios which we must estimate for the chemical risk analysis. The very objective of doing chemical risk analysis is to determine which process piping or equipment has the greatest potential for release of significant quantities of toxic chemicals. We are interested in estimating the maximum release of chemical or a toxic chemical in the airborne situation. So, one should result in evaluating several scenarios. You have to compare them, whichever gives me the maximum highest potential of release, that should be considered for the scenario. So, evaluating several scenarios will aid in determining the largest potential airborne release. Remember, in chemical release analysis, we speak only about airborne release of chemicals. Process conditions such as temperature, pressure, physical state and pipe size are very important. They should be considered as an important data or input for chemical exposure index, because they have a significant impact on the airborne release rates. Let us for example look at the scenario identification of the picture shown in the slide now. Let us say there is a bullet which may have a hole for discharge, which may develop a crack either on the bullet itself, or the crack can be on one of the pipeline or the valves. Now, this is what we call as a process pipeline. There can be a scenario where the process pipeline can rupture. For example, this is a pipe connection which is taken away from the bullet. This is the hole which is being used to draw or discharge a given diversification to the pipeline. This is a flange connection which connects the primary or principal pipeline to the further process pipeline, and there is a pump which actually pumps this chemical or this liquid further to any tank or anything. So, one can see here, this can be a ruptured pipeline, the valve can be ruptured or cracked, the pipeline can rupture, the hole can also release chemicals, the relief valve may not work properly, or the entire bullet can also develop a crack or a fissure because of over temperature and pressure present inside the bullet by the chemical. After given complexity of different scenarios, what scenario should I select for a chemical exposure index study? If we talk about process pipelines, it is generally understood that rupture of the largest pipeline in the given process should be considered. For smaller than 50 mm diameter, you must consider that the full pipe bore is ruptured. For a diameter of the pipeline varying from 50 to 100 millimeter, you can consider rupture equal to that of 50 millimeter diameter pipe. For greater than 100 millimeter diameter pipe, consider the rupture area equal to 20% of the pipe cross sectional area. So, these are recommended by chemical exposure index study for conducting different scenarios in a given selection of CEI. So, the same picture back again. So, one can now think of different scenario identification. Since the pipeline is now having a different diameter, maybe less than 50, 50 to 100, more than 100 millimeter, different scenario can be now justified for doing the pipeline study. It can be full bore rupture, it can be a pressure relief valve device which is directly connected to the atmosphere. You can calculate the total release rate at set pressure and temperature. All materials released is assumed to be 100% airborne because it is directly connected to the environment. The third scenario can be a vessel can rupture. The rupture based on the largest diameter pipe process attached to the vessel is to be considered for the criteria. So, for a given problem, the pipeline rupture, the vessel rupture or the relief valve rupture can be distinctly different scenarios for calculating or identifying the chemical exposure index. The fourth and the last can be a hole which is also ruptured from the vessel, where through the tank can overflow and spill. Once we know there are possible complexities of selection of scenario for chemical exposure index study, let us also see what are other scenarios present. The scenarios can be established based on experience. The contact process engineering for special cases can also be identified because it can include reactivity or mixture of chemicals based on which the chemical can release or become airborne. Treatment of instantaneous and very short duration continuous releases is simplified for the CEI calculation. Release from all scenarios, dear friends, please note, they are assumed to be continued only at least for a period of 5 minutes duration. So, after 5 minutes it is considered that some firefighting, some emergency response methods will be available in the plant which will try to mitigate or at least reduce or control this release to a larger extent. So, generally the scenario is assumed to be at least for a 5-minute duration. Let us now quickly see what are the guidelines for estimating amount of material which becomes airborne following a release. The moment I have a rupture either on the pipeline or on the vessel or on the pressure relief valve, these chemicals which are packed in a container or a vessel or a bullet will now become airborne. Now, I must have the guidelines for estimating what is this quantity of the chemical which is becoming airborne. The airborne quantity refers as AQ is the total quantity of material entering the atmosphere over time, directly as vapor or due to liquid flashing or pool evaporation. Friends, please note, the airborne quantity can arise from 3 sources. 1. The chemical can directly enter into the atmosphere. 2. It can become like a vapor. It can also become the liquid which is flashing or can also evaporate after the pool formation near the dikes of the chemical storage. CEI scenarios consider material to be released as liquid or vapor. CEI is not applicable for gaseous releases. Let us quickly see how the flow chart works for calculating the chemical exposure index. Let us say I have identified a scenario, or one can say I am not able to identify the worst scenario. You can identify this for all scenarios and compare the worst scenario in a given situation. So, identified a scenario, you have to calculate the airborne quantity. If you know the airborne quantity directly, select the scenario with the largest airborne quantity and calculate the CEI. If you do not know airborne quantity, first identify what is the type of release. If the type of release is gaseous, calculate airborne quantity using a separate equation, then select the scenario with the largest airborne quantity, calculate the chemical exposure index. If the type of release is liquid, calculate the liquid release rate. then estimate the total liquid released during a specific duration. If the operating temperature is lesser than the boiling point, then identify the pool size. If the operating temperature is higher than the boiling point of the liquid release, then in that case calculate what is called flash. Then estimate whether all material from the flash is airborne. If all of them from the material's flash is airborne, then calculate the largest scenario and compute CEI. If it is not so, determine the pool size. Based on the pool size, determine the vapor which is now getting evaporated from the pool, then based on that particular vapor concentration, calculate the airborne quantity, finally select the worst scenario and then compute CEI for the worst scenario. So, the comprehensive lookout of the flow chart for calculating chemical exposure index, which is essentially quantitative chemical risk analysis, is available to you on the screen now. Now, very interestingly, one should know what are the equations available to compute the airborne quantity if a scenario is identified. Let us quickly see now in the successive slides what are those equations available to compute different values of AQ, liquid rate released, flash point and vapor or a pool size, based on which a CEI can be calculated. Remember, chemical exposure index is a simple number which will tell me, which will help me to identify the risk based on a specific scenario. If you look at the CEI versus airborne quantity, there is a linear variation on a scale as shown here when plotted for ERPG 2 values on a logarithmic scale. So, CEI keeps on increasing with that of increase in airborne quantity for an ERPG 2 guideline given in milligram per cubic meter concentration, whereas airborne quantity is so many kilogram in a second. Please friends note that the minimum exposure of airborne quantity of chemical, if it is released, is 5 minutes. Let us talk about ammonia liquid release as a problem 1 to understand how do you estimate CEI for an ammonia liquid release from a container. Let us say ammonia is stored in a 12 feet diameter of a 72 feet long horizontal vessel under its own vapor pressure at ambient temperature of about let us say 30 degrees Celsius. The largest liquid line which is extracting out from the vessel is about 2 inch in diameter, which is 50.8 millimeters. Now, the required information to do chemical exposure index or chemical risk analysis are the following. One must know what is the pressure inside the vessel, which is the given data, which is 1064 kilopascal gauge pressure. The temperature inside the vessel, as you read from the problem, is 30 degrees Celsius. The normal boiling point of ammonia liquid is minus 33.4 degrees Celsius taken from the chemical engineering handbook. The liquid density of ammonia is 594.5 kg per cubic meter. CPB-HV is a ratio as available for all the chemicals available in the chemical engineering handbook. For ammonia, this value is 4.01 10 power minus 3. Height of the liquid in the tank is about 3.66 meter because the tank height is given as so many feet, which is 12 feet. The diameter of rupture of a hole which is extracting ammonia from the vessel is 2 inch diameter, which is 50.8 millimeter. The molecular weight of ammonia is 17.03, which we know from the chemical engineering handbook. Let us see what is the step 1 in estimating CEI. Now, in this scenario, there is a liquid release, it is not gas, therefore I must compute AQ. So, estimate the liquid release first. The liquid release can be given by a simple expression as shown here. Substitute the values of the diameter D 50.8, density which is given, gauge pressure which is available to me, delta H is the height of the liquid column of the ammonia being stored in the vessel, which is 3.66 meter. So, all of them are unit compatible. Therefore, if you substitute them in respective units, then I will get L, which is the liquid released ammonia in kg per second. For this problem, 61.9 kg per second. Once I know this, I would also like to know what is the flash fraction of this ammonia getting evaporated. The flash fraction is given by an equation FV, which is CpBHV T minus boiling temperature. Fe is now obtained by substituting the values of the above equation, and we know the operational temperature in the specific problem is 30 degrees Celsius and the boiling point of ammonia taken from Chemical Engineering Handbook is minus 33.4. Therefore, the volume of flash fraction in this specific problem comes to be 0.254. Now, if this volume exceeds 0.2, then airborne quantity is completely assumed to be the liquid. Since in this value Fe exceeds 0.2, that is 0.254, then the airborne quantity will be exactly equal to the value of L, which we computed from the last slide. Therefore, airborne quantity now will be 61.9 kg per second, which I computed from the last equation. Once I know this, I can now directly compute the chemical exposure index number, but chemical exposure index number is relevant to detailed difference of ERPG values. For ammonia, from the Chemical Engineering Handbook, one can find the ERPG2 concentration is 139 milligram per cubic meter. Therefore, Ca will be nothing but the equation as 655.1 multiplied by AE equal to ERPG2 to the square root of this value. So, I substitute the values because AQ is 61.9, which I got from the last slide. ERPG2 for ammonia is 139. I substitute in this equation, get Ci value as 437. Please understand, Ci is simply a number. Once I get Ci, one will be interested to know how I am converting this into term of societal risk. So, I compute what is called hazard distance. Hazard distance is a quantitative figure which tells public that up to what distance your life can be a threat. One can ask me a question, how will you relate the life threatening to that of hazard distance? It all depends on what ERPG level you are estimating. If you are estimating hazard distance for ERPG level 3, then it is life threat. Let us see for ERPG 2 of 139 milligram per cubic meter, hazard distance given by this equation, I substitute the values, I get the hazard distance in 4372 meters. On the other hand, up to 4.372 kilometers, if ammonia liquid is discharged from this vessel at a boiling temperature of so and so, then it will not cause irreversible effect on human being, because ERPG level concentration 2 says and states that it should not cause irreversible effect on human organisms. Similarly, one can compute hazard distances for ERPG 1 level. ERPG 1 level is the mildest possible concentration. For hazard distance will be 12.5 kilometers. So, it is very evident for up to 12.5 kilometers, if you stay beyond 4.375 kilometers, that is from 2 level to 1 level, you will not even get objectionable odor. On the other hand, if you are staying beyond 12.5 kilometers, you will have no effect of this liquid released in airborne content at all on the societal risk. For ERPG 3, which is the lethal concentration, which is very high, 696 milligram per cubic meter, the hazard distance comes to be 1.953 kilometers. So, if you are staying less than 1.9 kilometers from the plant, when the liquid is released or discharged at the given rate, then it is sure that you will have a reversible effect in your body, which may end up in fatal also. Let us take up another example, which is the chlorine vapor release. The first example problem was on ammonia liquid release. Now, I am working a problem on chlorine vapor release. Let us say I have an object or a vessel which has got a gas ejection pipe. We are having a liquid ejection pipe. There is a valve bonnet which controls the chlorine vapor release completely. There are 3 fusible plugs at each end of this container. The container is about approximately 7 feet long and the diameter is about 2 feet 6 inches. There are upper and lower gas valve and liquid valves seen in the figure respectively. Now, a 3/4 inch vapor connection on a given vessel, which is 1 ton chlorine cylinder stored at ambient temperature, has fractured. Now, the temperature is about 30 degrees Celsius, which is fractured, and the capacity available is 1 ton chlorine. Let us see what are the required information for solving this problem. Pressure inside the vessel is 788.1 kilopascal, which is given in the problem, which is the gauge pressure. The absolute pressure is of course 889.5 kilopascal. Molecular weight of chlorine vapor is 17.91. The temperature of storage is 30 degrees Celsius given in the problem. Diameter of the hole is 3/4 inch, which is about 19 millimeter. Step 1, determine airborne quantity of this chlorine vapor given by this equation. I know the values, substitute them, I am converting them into kelvins, substitute them, I am adding 273 here, substitute them and get airborne quantity as 0.74 kg per second. Now I want to compute directly the CEI. The ERPG level 2 for chlorine vapor is 9 milligram per cubic meter. I substitute the value, I get CEI as 188. Then I compute hazard distance for ERPG 2. I get hazard distance as 1.878 kilometers for ERPG 2. You can also do this for ERPG 1 and ERPG 3, which gives me the respective values shown on the screen. So ERPG 3 is as close as 0.74 kilometers from the plant source, whereas ERPG 1 is as far as 3.254 kilometers from the plant source. So any human being or biological organism living beyond 3.25 kilometers from the source will not be affected even by a odor of chemical release like chlorine vapor in the airborne concentration as shown in this example. So hazard distance gives a physical interpretation of how chemical release will affect the societal risk in terms of public health. This lecture has given you two examples, enable you to work out the chemical risk analysis for two different type of concentration, one on a liquid concentration, other on a vapor. One should be able to work out chemical risk analysis using the equations shown in the presentation. Thank you.